Alright, so I wanted to make a little video here to talk about timing of flip-flops and how that relates to timing of state machines. This was stuff we did not get to in class today. So let me just talk a little bit about this. So let's just take a simple idealized D flip-flop. We've got our clock input, we've got D going in, we've got Q coming out. And if we think of a timing diagram where time goes like this and our clock is clicking in some pattern like that, we know that our Q output responds to match our D input, and the D input can change and it doesn't affect the output until the next rising edge of the clock right here. And now the D input might drop and it doesn't affect the output until the next rising edge of the clock. So here's the deal. Each time the clock ticks, that's what these dashed lines represent. Each time the clock ticks, D is sampled and the Q output matches the D input. So there the clock ticked, D was high, so Q went high. Here the clock ticked, D was low, so Q went low. Okay, that's the essential behavior of these flip-flops. The changes in the output are synchronized to the transitions of the clock. Alright. So here's the ideal behavior of, say, a D flip-flop. But suppose D were to change just before the clock tick. So D rises and then just a little while later the clock ticks. A question is, how quickly can the flip-flop circuitry respond to a change in the input? What if we were to rise the D input just, a fraction of a nanosecond before the clock ticked? So there's the clock tick right there. But right before we change our mind and we say, oh wait, I want the D input to be a 1, is the Q output going to respond or not? And the answer is it's not going to respond if this happens too soon to the clock tick. So we have timing requirements on these flip-flops. The first requirement is what we call the setup time. And so the setup time is the distance from when the D input changes until the clock ticks. And we call this tau. We can say tau subscript SU for setup. Okay, so tau SU is the setup time, and that's the minimum time for which the input must be stable before a clock tick. Alright, so if the setup time is 5 nanoseconds, D has to stop changing at least 5 nanoseconds before the clock tick. Okay, if the setup time is 10 nanoseconds, D has to be stable at least 10 nanoseconds before the clock tick. It can be stable earlier, right? D could be set, right back here. We might have all this time. That's fine. But if this is the setup time and D changes somewhere sooner than that before the clock tick, we might get unpredictable results. So that's one criteria, is a setup time. The other criteria is, suppose, right here, D has gone low, and this was, within the setup time, so this was fine, and the clock ticks, Q goes low. Well, we know that somewhere out here, it's perfectly fine if the D input rises again. That's okay, it's not going to affect the D output. But what happens if we change that D input very, very shortly after the clock tick? Right? So right here, the clock is ticked, and almost as soon as the clock ticks, we change our mind and say, hey, D's going to be high now. Right? Can that cause problems? And the answer is yes, it can. So we need to hold the D input for a certain amount of time after the clock tick. Okay? And this time is called the hold time, so we can call it tau sub H. So tau H is the hold time, and this is the minimum time to keep the input stable, right, after a clock tick. So if we put those together, right, there's a setup time and there's a hold time, and together that defines a period around the clock tick. So let me just draw, you know, tau sub hold here. This is a time window around the clock tick during which D has got to be stable. It can be unchanged before that, it can be unchanged after that, or it can change before or after that. But within this window, tau set up before the tick and tau hold after the tick, D has got to be unchanging. Okay, that's the underlying timing constraint on these flip-flops. Alright, so what does that do for state machines? Well, remember our picture of a general state machine looks like this. We have memory, which is the state of the system, and some collection of that feeds our combinational logic, and the output of the combinational logic. So these are buses. I'm drawing these arrows with slashes on them to say that could be 2 lines, could be 20 lines, could be 1 line. Okay, the output of the combinational logic feeds the D inputs of the memory, okay, or the JK inputs, or whatever the inputs are to the flip-flops in here. You have external inputs which go into your combinational logic, and your combinational logic generates a series of outputs. Okay, that's your basic state machine. And remember, there's a clock, which we don't even usually draw, but there's a clock, and the clock is simply connected to the clock input of all of the flip-flops. And you clock all your flip-flops from the same signal. Okay, that's standard synchronous design. So this clock is pulsing high, low, high, low, high, low. And each time that it ticks, right, if these are positive edge-triggered flip-flops, then on each of these positive transitions of the clock, the inputs affect the outputs of the flip-flops. Those feed the combinational logic. Combined with the input generates new outputs from the combinational logic going back into the inputs of the flip-flops. But those inputs don't have any effect until the next positive clock edge. So here's the question in analyzing a state machine: how quickly can we clock this? How fast can we run this clock? Now theoretically we can run it as slow as we want. We can tick the clock, and you know, after 5, 10, 15 nanoseconds, the changes will trickle through to the outputs of the flip-flops, and they'll trickle through the combinational logic and come back in here. If we wait an hour from one clock tick to the next, no problem. The system will behave perfectly, but an hour per clock tick is really slow. On the other hand, if we were to tick this clock every nanosecond, we potentially have a problem. Now, if you look at the data sheet on a typical flip-flop, you'll see what these setup and hold times are. And they tell us, for example, that the D inputs can't change for, say, 5 nanoseconds after the clock tick. Okay? So after the clock tick, these inputs have to stay stable for a while. Well, that's usually not a problem because this combinational logic has its own delay, which we call tau sub p. Tau sub p is just a general propagation delay. And that's just a consequence of the fact that each of the gates in here has a delay associated with it. If we have an inverter, a change in the input does not immediately affect the output. It takes a few nanoseconds, maybe 10 nanoseconds. And if we have an AND gate and both inputs are 1s, and now one of the inputs drops, the output will drop, but not right away. It might take, 12 nanoseconds. And since we have gates feeding gates feeding gates, there's some considerable delay in here, 20, 30 nanoseconds, maybe considerably more. Okay? And so the D inputs to this are usually going to be unchanged for a while. So the hold time is not usually an issue, but the setup time is critical. The setup time tells us that once these outputs have changed, which is whatever the propagation delay is for the flip-flops, and the logic has trickled through all of this combinational logic, which is the propagation delay for this block, and they've gone back around to set the inputs of the flip-flops, Now we need to wait an additional amount of time, which is the setup time. And then and only then, or after that, can we allow the clock to tick. So if we tick the clock 1 nanosecond after we've changed, after the last tick, right? Chances are the outputs of the flip-flop haven't even gotten set yet. They certainly haven't had a chance to trickle through the combinational logic and go back into the inputs of the flip-flops, and they certainly haven't had time to satisfy the setup constraint. And so ticking this every nanosecond, we're going to get gibberish out, right? It's too fast. So how long do we have to wait? Well, typically, the amount of time it takes for the propagation delay through here, and I can include the time it takes the flip-flops to respond in this propagation delay, plus the setup time. And so the clock period has to be bigger than or equal to this, which means the frequency has to be less than or equal to 1 over the reciprocal of this. Okay, I'm not going to go into figuring out periods and frequencies and how they relate to each other, but they're basically reciprocals of one another. But the units are always weird, right? So if your period is 1 nanosecond, that's a gigahertz. If it's 10 nanoseconds, that's 100 megahertz. That's a different topic altogether. But timing-wise, right, basically our fundamental constraint is the total propagation delay plus the setup time. That's the minimum amount of time we need from one tick to another. So our clock period, right, and our clock period is, you know, from one tick to another, that's clock period, has got to be at least the sum of the propagation delay plus the setup time. And the hold time usually doesn't come into play. It's usually so small compared to the propagation delay that will automatically satisfy that. Okay, so we can use this to analyze machines, and there's some homework questions on that that ask you how quickly you can clock. There's also some questions that ask you to look at a timing diagram and show, you know, what these windows are around the clock ticks based on the setup and hold requirements for the flip-flops. And let me just show you a typical data sheet just to kind of round this out. Alright, so here's a typical data sheet. This is from Texas Instruments. This is for inverter. So for AND gates, OR gates, inverters, we find data sheets like this. If you scroll down to a section labeled something like switching characteristics, you can see propagation delays. So here's the propagation delay for a low to high transition. Okay, this is the delay from a change in the input to the output. And when you're going from low to high, typically it's going to take 9 nanoseconds, possibly as much as 15. To go from high to low, it's going to take you typically 10, possibly as much as 15 nanoseconds. So we can calculate our propagation delay in a logic block by basically adding up the propagation delays each time we have one gate's output feeding the input of another gate. And it's a bit of a combinational problem, right? Figuring out what's the worst case propagation delay. There may be a situation where one input trickles through, you know, 5 or 6 logic devices, and you have to use those propagation delays to find the worst case propagation delay for the whole circuit. There's software that will help us do this, but it's in general a fairly complex thing if you have a complex circuit. Alright, now if we look at a typical flip-flop, this is a 7476 dual JK flip-flop. We can scroll down and look for switching characteristics on this, and we'll see propagation times from low to high or from high to low, and they're larger, right? They might be 16, 20, in some cases as much as 40 nanoseconds. So considerably more propagation delay there. And then down here we can see the setup and hold time. So recommended operating conditions. Setup time before the clock. These are negative edge triggered, so the clock drops for the action. So setup time before the clock, minimum 20 nanoseconds. Could be as long as you like. And then after the clock drops, the input needs to be stable for, and it says the hold time is actually 0 nanoseconds, which is not surprising. But the setup time is critical, right? So once all of our circuitry has processed the changes in outputs and all of that propagation has happened, and now we have the inputs to the flip-flop set correctly, now we need to wait an additional 20 nanoseconds. And after we've done that, then everything is stable, ready for the clock to tick. So those go into calculating our maximum frequency that we can clock a state machine at. All right, hope that helps. Thanks.